An honor to, and yes, recording in progress, got it. I'm going to give you a kind of general overview of my own view of where we are in quantum computing. It will be kind of hardware oriented, so I will not talk that much about algorithms, but I hope I will give you an interesting perspective on how the machines are developing and what physics we encounter in working to create these machines, and where the obstacles are, where the really hard work is. And there's definitely is lots and lots of hard work ahead, but I think things have become clearer actually in the last couple of years in what the trajectory might be in the creation of these new kind of computing machines. Now, let me take a moment and share a screen, and I'll take you through PowerPoint for the remainder of the hour. Let's see, yes, and there it is. So current challenges for quantum computing. So I'll begin, I'm going to jump right into a kind of historical story, that is, take you back 60 years and examine the words that were spoken by Richard Feynman at the American Physical Society that year in 1959. Now, Feynman is often acknowledged as sort of the forefather of quantum computing. I think with some justice. I think he did indeed, identify this as a possibility long before anybody else did, and it was part of a larger agenda that he had, which was to advance the science of computing, and he's well known to have done that in various ways. But this work in 1959, which of course could not be followed up very rapidly, offered a manifesto, and it is often also stated as a manifesto for the area of nanosciences and nanotechnology, because he says here that well, there's plenty of room at the bottom. That was the title of his lecture, and so. By bottom, he meant the bottom of, among other, a few other things, length scales. And so he foresaw that computing devices, other interesting machines. He actually also talked about electric motors, I believe, in this lecture, but also about computers, that he had in mind electrical devices with small numbers of atoms. And he recognized that he didn't know how to design such things, or that he couldn't use the thoughts that engineers have about designing electric circuits or designing mechanical structures because of quantum mechanics. And he talks about that we need sort of different ways. I think he didn't really know where this was going, but he recognized that some concept of quantized energy levels would be important. He mentions the spin angular momentum, but those are just a few hints that he gave. Now I'm going to jump from that to the event that occurred 35 years later, and which very much was crucial in the development of this. And I realize at this stage this is sort of halfway further towards the present, so it's already quite some time in the past now. But when I saw this happen myself, when I was a scientist at IBM, I thought this was a great revolution, this discovery of Peter Shor, that, to give it in a very short language, he recognized that there is a quantum evolution, the quantum computer, as Feynman had named it some decades earlier, that would step by step manipulate a quantum state to make possible a very difficult computation, and very difficult in a specific way. And what I'm showing here is the an example computation of prime factoring. So this is the RSA 129 numbers. This is a 129-digit number, which was offered as a prize problem, I guess in the 1970s, and the cryptographers who offered this as a puzzle said, I guarantee to you, this is a product of two prime numbers, and find the prime numbers. And this was done. It was possible to do this with classical logic, with large conventional computing project. But Shor discovered that with the right kind of quantum dynamics, stepwise executed, that after a very, a short number of steps, short in the language of computer execution, that the same problem could be solved. Now, it's interesting to reflect that this was definitely a turning point in this subject of quantum computing. It made it clear that it could do something real, that, those of us who looked at it saw, it was clearly based on our principles of quantum physics. And in fact, I would claim that absolutely nothing new had developed in quantum physics from Feynman's time, from 1959, till this time 35 years later. So in other words, Feynman could have, upon some kind of reflection, discovered this also 35 years earlier, because it just was based on standard quantum mechanical principles that he knew very well. And so, one might ask, why did it take 35 years for this theoretical insight? And I think it had a lot to do with maturing of the use of quantum theory, that even a wizard like Feynman somehow took a long time for him and others to believe that the quantum theory should be taken so literally as it is in the work of Shor, and that it required an act of daring to imagine that you could control quantum evolutions in such a detailed manner. And but I'll show you now in this talk, and I can come to the outline of my talk, what it is that I mean about the complex manner of manipulation that is implied by Shor's algorithm, or implied by the little symbols that are shown here that indicate the occurrence of entanglement in a controlled fashion, in the controlled change of the state of a set of qubits, a state of spins, but I'll come to that in a moment. And I'll show you how, indeed, in 1994, the possibilities for doing this experimentally were almost nil, were only the very tiniest bits of this quantum process, of this computer, this quantum computer, were at all possible in a laboratory. And I'll tell you, the main aspects of my story will be to tell you how that is gradually becoming possible. But that from where we are today to doing, let's say, RSA 129 is the name of this number, I would say will take about an improvement of about 10,000, going from the hardware that exists today, which I will review in the course of my talk. So we're still way, way, way far from being able to do this. And in many areas of physics, you would say, getting 5 orders of magnitude is something, hardly possible. But this is computer technology. And so I think it's not so impossible to even today to draw a timeline of how we will get to this, tremendous further improvement of hardware. So that's a bit of a preamble to take me into this this outline. And what I will not do is tell very much at all about the current ideas of quantum algorithms. I've told you the big highlight algorithm, and there are at this point many others, but it's a very difficult subject, in fact, to find algorithms that will work today, on the kind of hardware that exists today. It's much easier to dream about the hardware that's improved by many factors of 10 and say what you will compute on that. That's a very easy matter because Shor and other mathematicians have laid out a whole set of very interesting mathematical problems that are cracked, that are made conceivable, or that are computationally tractable with quantum computing. Okay, but what I will do is spend time talking about what are qubits, this is part of the, the education that we had to go through, that we had to take our quantum concepts and seriously reinterpret them as concepts for computing. So here's a little diagram, I'll take you through it, of contrasting the world of bits with the world of qubits. So when we say a bit, we mean just some object. Well, it can be an abstract thing. It can be some just information theoretic objects. But I want to stick with the idea of physical embodiments of these objects, where, and a bit by definition is something that it has one of two states, a 0 or a 1. And I've sketched several embodiments. Some of them are just for fun, so to speak. One of them, let's start with this one. One is the presence of, say, a particle in one of two metastable wells. And this is an abstraction for many things in the here and now. Okay, and the 0 state, say, will be the well, the particle stuck in one well, and the 1 is a particle stuck in another well. And if you think of this as a certain amount of charge, then this is a, not terribly incorrect, a reasonably plausible description of a piece of flash memory, of a bit in a flash memory, where, in a flash memory, you have maybe 10,000 or 1,000 electrons either present or absent on a floating gate. And so that giving the, the 0 and the 1 of that bit of flash memory. I show others here. So in communications, especially, we use photons or light radiation, and it can be that you can encode a bit in polarization. So horizontal polarization of radiation can indicate bit 0, and the vertical polarization can indicate bit 1. And I use the word photons, but well, if you're an optical engineer, if you're a communications engineer, you don't talk photons, or if you do, you have to talk many photons in communications pulses. Here's one which is already depicted at sort of the microscopic level. If you have an spin, but let's talk for the moment magnetization. If you have a magnetization in some material which is pointing up, that can indicate bit 0, and pointing down can indicate bit 1. As we have in magnetic disk drives. So we have all these realizations. I also, for fun, throw in Schrodinger's quote bit. No claim that this is of any use in any real technology, but we have live cats and dead cats. Now, the idea of a qubit is to say we apply a quantum mechanical, hypothesis to this, and we say we should also allow superpositions of these as legitimate data carrying states. Or said in a more fancy way, we want to say 0 and 1 are now basis vectors of a Hilbert space, and our states can be vectors, complex valued vectors in this Hilbert space. So here's the block sphere of those. And so that has various meanings in for these different physical realizations of the bit. And so here's, and I didn't make this up, this is from somebody's paper on Schrodinger cats, and they say, well, maybe you should imagine states which are equal superposition of alive and dead. I think we could agree, I mean, those of us who are serious about these things could agree that this is a totally impossible state. The reason being that it does not take account of the extra degrees of freedom in the environment of the cat that also should be properly written as a correct quantum state of any Schrodinger experiment, thought experiment. So this, in short, is a very, very poor qubit, and we will never again talk about such a macroscopic object as a qubit. Likewise, the state of 10,000 electrons in the flash memory, it's also very implausible that they could be placed into a coherent quantum superposition. However, if you replace those 10,000 electrons by a setting where you have only one electron, then it's indeed very plausible that you could make because of the phenomenon of quantum tunneling, that you can indeed have an equal superposition of an electron present in two wells in a structure. And it's been done, and I'll sort of review one or two of those thoughts in a moment. This is not indeed the most coherent qubit. That is, there are still problems with how this correlates with the environment. Much clearer cases are ones of this case. I talked about it macroscopically, but if you say, let's consider the magnetization of a single electron, so the spin angular momentum of a single electron, then it's quite a commonplace thing to say that, of course, the electron spin does not only have the +1/2 state and the -1/2 state, but it can be in any superposition of those. I sketch here, the eigenstate of the Pauli X operator, for example, and that's in many settings just as equally good a quantum state as any other. And so for, the spin of an elementary particle, this a spin 1/2 elementary particle, all vectors in the Bloch sphere are, equally reasonable. And there's nothing a priori that selects out the 0 and the 1, these z-axis basis states as, the most important, feature of these as information carriers. And so that has indeed been a pretty plausible qubit. And then the last one is that, likewise, if you can, create sources which emit one photon at a time, then it's sort of, again, equally plausible to be anywhere on the Poincaré sphere of polarization of that photon. And so that's also quite a plausible qubit. Now, of course, we always talk about the qubit in terms of the Bloch sphere and about the states on the Bloch sphere, but it's actually essential that the states are not only those, but are states that work in that Hilbert space, but can be entangled with other identical objects, other qubits. And it's that, it is those registers, multiple qubits that create the setting for quantum computation, and, in a sense, are the basis of this tiny sketch here that, each of these lines is meant to be sort of the world line of a qubit, and these diagrams, which we talk about from a computer science point of view as logic operations, are actually sort of controlled scattering events that create entanglement between those qubits. And so, but needing many, many qubits, millions of qubits to even represent the problem and to execute the dynamics that were specified by the Shor algorithm. Okay, so so onward from that, so I thought I'd immediately talk about the case of single electrons and also the spins of those single electrons, because this idea of going all the way from flash memory to something that in which the quantum principles are clearly applicable, that is in this sketch, were indeed actually accomplished pretty far back. And the reason why I mostly won't talk about this is that subsequent progress has not been as fantastic and as in other fields. So I should say that I'm very prejudiced towards solid state implementations. I mean, I'm a condensed matter physicist by training. I do truly think that they are the promising approaches to achieving quantum computers, mainly because you will be able to use chips. You can make things on chips and use the incredible power of the semiconductor industry or fabrication industry to make very, very complex devices on chips. So that I realize that leaves out vast and incredibly interesting areas of science in neutral atom physics and in ion trap physics. And I think those are also interesting and indeed possibly promising. So, but I will confine myself today to solid state things. So this is a sketch of a microstructure. It's not actually particularly on a small scale. But the important thing is that in these kind of structures already in the early 2000s, it was possible to create structures which had in this region of the chip, because of the voltages that could be applied to electrodes on the surface of the chip, you could really arrange conditions such that there's exactly one electron in the left part of this structure and exactly one electron on the right. So this is a double quantum dot, as it's called. And these sketches or these diagrams on the right are indicative of those, that there's it's a very bad color choice for this description, that there's a region of this voltage diagram where indeed you can determine by sensing that there are exactly two electrons present, one on the left and one on the right, or other conditions if you want two on the left and one on the right, etc. And so this was an exciting development, and there were immediately some experiments attempted that would indeed use the spins of these two electrons and entangle them and control them and show that you could do 2-qubit gates on them, and they've all actually worked. The further problems are, well, other technical things, but I'll reserve the last half of my talk will be very much about, I'll say, quote, technical things about machine building, because I would say the basic physics works. We can make 2 qubits in any number of ways, and we can entangle them. And the big challenge has been, how do you make more qubits, and how do you, what is actually needed to control them and to run algorithms on them. And has many special difficulties which are overcome in other approaches, at the moment rather better than in this approach. The physics works great in these systems. But instead I move on to another one, and this is yet a different kind of sort of classical to quantum transition than the ones that I sketched in my introductory proposal. That is that, that since we're working on chips, it's plausible to say, can you make things from circuits? And in fact, with electric circuits, it's pretty easy to make a harmonic oscillator. So I'm sketching a harmonic potential, but that is in fact just a circuit that you would make by joining an inductor to a capacitor. And you can even make it quantum mechanical, although that requires low temperatures for it to be at temperatures such that, let's say, kT on this energy scale is in fact small compared with the energy spacing, the quantized energy spacings of these. But it turns out it is possible in the microwave domain of, that is, you can both make electric circuits that are good resonators, LC resonators, in the microwave domain, and you can make refrigerators that get you to the appropriate temperatures, which are millikelvin temperatures. I'll come to more of that later. Now, harmonic oscillators are not the most interesting quantum mechanical objects, but you can use physics of superconductors to have, a special kind of nonlinearity of inductance, which is also called Josephson tunneling. I'm not at all going to talk about the physics of Cooper pair tunneling, but why that produces, this specific kind of nonlinearity in inductances. But in fact, it does to very high accuracy, and it does it in such a way that there's negligible resistance in any of the circuits that are talked about, and which I will show you. I'll show you very complex implementations of such circuits in a moment. And by that, you can get, nonlinearities in this harmonic oscillator, and getting non-trivial spacing arrangements of the energy levels in this. And that permits you to spectroscopically isolate and remain within the manifold of the two lowest energy states of these. So that's sort of quantum mechanical from the start. That is, there's no easy classical analog of what you're doing in this device. This is the jargon of this is called the transmon qubit, and it's been very successful. And I'll be telling now a little bit of the story of how that's developing into, new kinds of systems. The heart of the transmon is a sort of nanotechnology. You have to evaporate some some superconductors on top of each other with the right kind of oxides in between. But in fact, it's a pretty old, it's not the most advanced kind of nanotechnology. It's, in fact, people have done this in the fabrication laboratories for many tens of years. So, and we continue to ask, like, well, should we really move on to the newest kinds of nanotechnologies and materials? But they haven't so far been so important. Important transition currently is that these have always been done with aluminum, and it turns out that tantalum seems a little bit better. But in fact, the simplest materials seem to be the best. So no high TC, cuprate materials, all far too complicated and with far too many defects, in fact, is the big problem. Okay, now, given that, now I'll switch to sort of the grand picture. This is sort of at the advertising level, that on the basis of this physics, the fact that you can make coherent 0-1 structures and couple them together using electric laws, using the ideas from electrical engineering, effectively, have permitted now some real quantum computers to be made. Well, this was the hype, as of pre-corona hype, but the hype continues, I would say, of quantum gold rush and everything. That these big organizations, unfortunately not in Europe, we say, IBM and Google have been busy making, real quantum computers that really do things. Now, how real, or what does it mean that they're real? They've at least entered the consciousness. Well, I don't know how extensively, but I do seem to find that these devices, these instruments have become a little bit kind of even pop culture, that you see people say, do we have quantum computers? You say, yes, we have quantum computers. Oops, sorry. And here they are. Now, I do like to deflate that a little bit. This is a nice demonstration model that IBM showed for their 50 qubits. So indeed, we've jumped up, and I'll talk about these a little bit, or about what kind of considerations go into making a 50 qubit device. But one comment to be made is almost the entire thing you see here, and let me do it this way. I can't do it that way. Okay. Almost the entire thing that you see on in this diagram is a pretty conventional helium cryostat, helium dilution cryostat, because the main technical necessity is to get the quantum harmonic oscillators, these Josephson devices, held at low temperatures, not merely below their superconducting transition temperature at a few Kelvin, but actually much lower than that, really to satisfy this condition that you need temperatures to be far, far below the excitation energies of these individual devices. And that takes you to tens of millikelvin. But these are the kind of instruments that will do it. And in an instrument like this, the sample volume down in this region, if you can see my sketch, is held at tens of millikelvin. But if you ask, where's the quantum stuff happening? It's only a little chip, centimeter-sized chip, just at the very, very bottom of this whole thing. And all the rest of it is, the refrigeration infrastructure, but also the instrumentation infrastructure that gives sufficient control to these 50 qubits. And control means actually all the things that you need in a regular computer, only in quantum language, you need to be able to, clear the memory, initialize the qubits to, say, to their ground state in physics language. But you also need to be able to apply gates. And by the end, I'll show you, what does it actually mean to apply gate operations. And you have to keep noise out. And these whole stacks of things are all filters, basically, are all isolators. I'm hearing a bunch of noise, which I presume is not someone trying to interrupt me, but getting themselves muted. And then there are all sorts of hand-wired things, because you need many, many wires to connect this to the top of the stack, which is room temperature. So you have a little tiny chip, centimeter-sized chip with 50 qubits, which is not at all a demanding piece of fabrication. I mean, you don't need a chip foundry. You don't need NVIDIA or Intel or anybody to make such a chip. It can be made in a very easy, in a simple fabrication laboratory. But the control apparatus, however, is quite extensive. I mean, well, I'm talking at CERN, so you know about extensive control apparatus or instrumentation. But here it's at some scale, this is coming. I mean, the instrumentation is far more complex than the quantum device itself. And that will indeed be much of the theme that I'll pursue as I go further. Now, let me zoom in and I'll now jump back a little bit in time. This is a picture from a somewhat earlier generation of IBM's chips, just to give you an impression of what's going on the chips themselves. They don't, these companies at least have started to become a bit proprietary. So if you say, can I see a picture of Google's 53 qubit chip? The answer is no, you may not. They show you just sort of cartoon schematics, and I don't know of anybody who gets to look at them. There is another aspect of it that the newer chips are packaged in very complex ways, so that much of they are now multi-qubit, multi-chip modules, and so you can't actually see when the device is really completely created. You can't see it because it's covered by additional layers of chips. So, but in the 16 qubit time, it was all done on one planar process. Now these are, they're on silicon chips and they're metallized, they're aluminum metallizations. However, they're otherwise not really like, CMOS transistor chips. For one thing, the metal structures are much less miniaturized than they are in ordinary chips. So these are in fact visible to the naked eye. So there's nothing nano about them. The only nanostructure are the Josephson junctions themselves. I'll come to that in a moment. And this is all superconducting at the temperatures of operation. Let me just take you through a few more things. This is, a 16 qubit chips where physically are the qubits, and oops, I'm sorry, I'm just doing the wrong thing. Let me jump here first. Oh yeah, I thought I had another view. Yes, sorry, I jumped a little bit too far. So this is, I've colored in white the actual locations of the qubits, which are in fact where these nonlinear resonators are. The rest of these, and there are indeed 16 of them in this ladder structure. Now, there are many, many other things going on, all these squiggly things going on in this chip, and mostly they're microwave technology, you might say. But, well, one way of saying it is that they are, they are conceptually, many of them are just couplers. That is, there's a transmission line that will carry a photon from this qubit to this qubit. Now, it's all tortuously, it's all snaking around, and that's only actually for sort of space considerations. That is, you want it to be a certain length to meet some resonant condition. And to get that length, you fold the wire up on itself. It's a transmission line, however, not just a simple wire. So a fancy thing you can say is that the way that entanglement is mediated between these two qubits, here and here, is by the passage of a photon, but in fact a virtual photon, along this transmission line from here to here. But you have to activate that process by certain pulsings of the systems, which are accomplished by delivering pulses of radiation. Whoops, I wanted to go back. Whoops, not that far back. Pulses of radiation which come in here. And again, because of some resonant conditions that you want to meet and filtering conditions, this is itself another resonator, but built with quite standard microwave technology. That is, high frequency analog devices would have all these kind of elements to them. These resonators off to the side also have a dual use. They are in place to measure the state of the qubit. So the right kind of pulses delivered into this resonator and then reflected out and detected on the outside world will tell you the state of the system when you want to know it. So that's the readout aspect. There's also a folded up resonator that connects qubits in this direction. So you have sort of full connectivity in a ladder of structures. And so just a few other words about this. This works, you know, pretty well. The people have been running real algorithms on this, and it's scaled up version of this, and have even shown quote supremacy, shown you know, things that this device can do that are otherwise very hard to simulate on an ordinary computer. This is a little bit of a summary of this thing that if you look at this whole picture, it has in total about 46 resonant structures, but 16 of them are these, I'm trying to gesture here. Sometimes my pointer works and sometimes it doesn't. 16 of them are these very nonlinear resonators that I've highlighted, which can at most contain, or will at most contain, one excitation, but one quantum of radiation, basically. 30 of them are these normal coplanar waveguide resonators, but which sometimes are only there to carry individual photons, carry them even virtually, or sometimes indeed just a small number of resonators. The quality factor of these resonators is always very high, so the amount of resistance on this chip is negligible. And there are almost no stray photons anywhere in this structure. There are no thermal photons at all, so there are very few thermal excitations of any kind. Well, they're thermal phonons, I guess, in the silicon crystal, but they do not couple to these degrees of freedom. And other thermal radiation is rigorously kept out of this device. It's in a very dark environment. It's also actually held in a very, very low magnetic field environment. That's part of the shielding aspect of these devices. Okay, so a lovely, wonderful, amazing piece of technology. A few things get hard. Well, let's see, where do I want to go with this next? Okay, I'll feature, okay, one research problem that still goes on in this is that let's see, the qubits, as I said, are intended to, you know, they're on purpose connected in this ladder structure. So this is on purpose connected to this and can on demand be entangled. That is, you can on demand activate the virtual photons in this link that make it possible to entangle them, and also this link and also that link. But unfortunately, there still are some couplings elsewhere that are not supposed to be there. And this has been a big headache for IBM, and and you can say, well, why is it there? Or, I mean, there isn't any on-purpose resonator connecting these two. There's no, you know, obvious direct route for a virtual photon to pass from this qubit to that qubit. And the coupling's not very big, but it is still many line widths, so it's still sort of spectroscopically relevant, and you have to really think about and work on the question of how relevant might it be for the operation of this as a computer. That is, in my another part of my talk, I'll say just a few words about fault tolerance, and luckily, quantum computing can tolerate some degree of imperfection, like imperfections in the occurrence of couplings, but not very much, though. So it's remains a little bit of an open question of how well we can ameliorate these, you know, this specific erroneous coupling. I can say that, well, I posed the question, where does this coupling come from? And the answer is from pure electrical engineering, I would say, and I'm just for a moment featuring some of my own recent work in conjunction with IBM scientists to say that the problem of coupling, now this little equation in the bottom is sort of the quantum part of this, that is that what you'd like to say, going back to here, is that there is some coupling here. And because of this, well, the virtual coupling that's present, there is finally an effective coupling between these two-level systems, these two-level systems. So you can talk about them in spin language, and we say, well, this is indeed some spin-spin operator, some XY coupling, we would say, in spin physics, and it has some strength. And that's the thing that I say is like a megahertz, whereas intended couplings are quite a bit larger than that. And we say that that quantum mechanical coefficient is actually given by pure electrical engineering properties of this chip. So it involves the imaginary part of some transimpedance. Now, how do you know this? And it's just a transimpedance of the metal structure itself. And so we give a derivation using, well, an interesting mixture of quantum and classical electrical engineering reasoning that says that this is a formula that will take you from this impedance to actual predictions of these stray couplings. And this was a proof that was done that this really works. This, first of all, shows here's the chip again. And if you want to know things like these transimpedances, well, you have to do some, either measurements, but actually in the industry that cares about this, it's much more likely you do it with quite sophisticated simulations, microwave simulations. And this is a picture of the, an actual finite element grid that's used to actually simulate the relevant electromagnetics in a certain region of the chip. And you apply our formulas and you get a prediction for a whole bunch of possible, instances of stray couplings among different pairs of qubits. And then there are ways of indirectly measuring these as well, it turns out, by actual probings of the chip itself. And we find, I think this was indeed, when we did this a couple of years ago, the first time when there was actually very good correlation between a measured quantum mechanical property of these indicative of stray couplings and the classical physics, the classical electromagnetic physics in this case, that we say is indeed the origin of these imperfections. So this at a system level is filled with such imperfections. And so there's tons of things for engineers, but very well-educated engineers who actually also know quantum ideas to apply, optimizing principles for which come largely from the science of high frequency analog precision electronics and transfer those to actually making these chips work. And there are many groups, and well, including physics groups, have whole PhDs devoted entirely to the problem of better packages, of how you put these all together into a structure that will ameliorate these kind of couplings. So let me move on. I have basically two other areas to discuss with you this afternoon. One is I'll do very briefly, and we'll touch on this area of faultiness. That is, I've said, well, there are faults, we know how to reduce them, but quantum mechanics is a very picky thing in the sense that, well, you have an interaction that's wrong and you let a system evolve for a while and it will evolve to some other state than the one you want it to. And so will it evolve to a state that's so wrong that it won't give a proper factor in the Shor algorithm? And this has been worked on quite extensively and has now a long history, but I come at it in the following way, but my comment about that is here. But this tells the story of how various types, but mostly the so-called decoherence types of errors, have been remarkably improved over the history, the timeline of these superconducting qubits. So you have to know from this that the first reported superconducting qubit was in 1999, and it had a so-called coherence time, which is the the time to error, you might say, which was about a nanosecond. That's this one point here, which now, of course, we use an actual physics language for this. This is the language of nuclear magnetic resonance, say, where you would call this a T2 time. And this was just barely good enough to see any quantum effects, but with improved designs, it was possible to very quickly improve matters and improve this coherence time by many orders of magnitude. And it has, over the course of well, as you see, over the course of, first of all, 10 years, it jumped up by 4 orders of magnitude. So it was just a matter of sort of focusing on this, but this was the essential need of the experiment, because if you're only doing physics of Josephson tunneling, you don't need quantitative improvements of these coherence times to see your physics. But if you want quantum computation to run, you definitely need to focus very strongly on quantitative improvement of these kind of parameters like T2. And that was achieved. So that was, over basically 6 orders of magnitude. So we jauntily call this a Moore's law for this parameter. So we were tremendously advancing. Now, one thing to tell, you see this is a chart that ends in 2015. You can ask what's happened since then. And well, the Moore's law has ended. There actually has been very little improvement in the last 5 years in this coherence. What I also give here is a sort of fuzzier thing. I mean, each of these dots is a specific, paper. These darker blue things are kind of a judgment call, which was at any given time, could you do this more than once? And could you do it with more than 1 qubit? And that was also promising. This chart represented my personal prediction 10 years ago that this wouldn't progress so well. And actually that has kept up. That's done a bit better than I had initially anticipated, that these techniques for finding improved coherence have turned out to be pretty robust and easily transferable to other laboratories and to improved designs. The problem is that to do a Shor's algorithm, this figure of merit naively would have to be another 14 orders of magnitude bigger. So you need other principles, and now they've been under development for many years. And I can refer to work that began with Kitaev and Preskill, but a whole host of many important physicists took this on, and it's very connected with topological ideas in quantum physics that have been greatly advanced by this sort of need for solving this error correction problem. Now, as I say, this is not indeed a focus of what I'm going to say, and in the interest of time, I will certainly say less about it. I'm actually going to come back to that picture, but the picture that was given to us, and this really came to us from Alexei Kitaev, that he introduced the so-called surface code, which said that if you had a two-dimensional lattice of qubits, so IBM was doing these ladders, but in fact they have progressed towards really fully two-dimensional designs with great engineering difficulties. Then you have a scenario where as long as you allow half of these qubits to be sacrificial, so they will not participate in quantum computation at all, but they'll be measured frequently to diagnose what's going on with the rest of the qubits. But you go through a regimen that strongly entangles the rest of the qubits, the white sublattice of qubits. What's shown here are just the initializations of these qubits. This should be in the 0 state, and this one should be in an equal superposition of 0 and 1. But then with a regimen of entangling operations, you get this into a so-called topologically ordered state. And this is believed to be the golden route to quantum computing, that with unfortunately quite a lot of overhead, that it has the promise, or really every hope is pinned on the possibility that it will, by introducing topological order in the system, permit this enormous increase in the effective time to failure. Now, first step has been taken towards this. Of course, in these corporate labs, these Google and IBM labs, they've taken farther steps. But again, you have to go to academia to see, sort of a fully explained version of this. And so this is the sort of first version of these square lattices that have been produced actually at the Technical University of Delft. This is, in fact, their latest report on these. And this is a chip of theirs, which is, again, the same kind of thing. There are these qubits. This is colorized so you can see qubits. Let's see. Yeah, in fact, I have a pointer, but I, again, can't have it on. There are, as in Kitaev's thing, there are these ancillas, these 3, and then, but in a square lattice, in another sublattice, there's a sublattice of so-called data qubits. And this is for 7 qubits, but in fact, they're quite hard at work on the same thing for 17 qubits. But certainly for university lab, this is stretching it. Not necessarily because of the complexity of the chip, although the chip is complex and has many electromagnetic issues that one has to deal with, but the instrumentation is complex and expensive to go far beyond these numbers. So I've talked about that, and well, this is just saying how good does the sort of raw error rate need to be, and the main message is that the transmons, the ones that for which I sketch these coherence experiments, that up near this level, that's around this 1%. Oh, I've said it here, in fact, that there is this so-called noise threshold, and we're somewhere near it. It's not totally clear where it will sit, and you want to be pretty well beyond the threshold to efficiently use these error correction techniques. But that's coming along. I can somewhat take credit for realizing that there would be, in more than 10 years ago, I wrote out pretty sketches of saying, the people who at that time were doing 2-qubit experiments will eventually be doing these whole kind of wallpaper layouts of qubits with arrays of resonators and qubits. And it's clear that if you were given a picture of the Google 53-qubit chip, which we don't get to see, it would be something along these lines. The details of how the resonators are laid out and the qubits, I'm certain, are different, but this principle of more or less regular repetition in order to take advantage of the possibilities of two-dimensional topological quantum physics have indeed carried the day. I'm going to skip around a little bit because I want to get to the fact that I've barely exposed the actual technical complexities. You saw the pretty picture at the beginning of this chandelier, some people have been calling it, this instrumented refrigerator. And what's really going on? This is a schematic, this again from the Delft laboratory, and it's again old because it's only the instrumentation of 1 qubit. Oops, sorry. So here's the 1 qubit in this schematic, and all the rest of this, all these, these signal flow diagrams, these all represent microwave lines. And this is what you have to do to instrument 1 qubit on a chip. Now, recall that the Shor algorithm is believed to take some number like 5 million physical qubits. And so you need a channel, a set of channels like this for all, 10 million of those qubits. And these are all precision analog hardware. And certainly as of 2012, these were all benchtop instruments. They're indicated by which manufacturer you get them from. Some of them are cards, but notice this is all in the 300 Kelvin world. There are amplifiers. At the very low temperature world, even at the low temperature part of this world, there are some instruments, quite special instruments, low noise amplifiers primarily, and isolation devices that are bulky and expensive. I'll give you some notion of the expense in a moment, but it's felt pretty certain that all this has to become obsolete if 10 million qubits is to be possible, because this would be the budget of Switzerland would be devoted to all the electronic devices, and you would need a football stadium to put all these boxes that were needed to control this 1 qubit. So this is going to go sort of special purpose, basically, that these were off-the-shelf instruments, and they were pretty well adapted to this. It was good that Google, when they did a 9-qubit experiment, which was also meant to demonstrate some error correction principles, also went to the trouble of telling the story of their electronics channels and also showed some waveforms. So this is just to give you an idea. These are 23 channels of waveforms that are needed to control 9 qubits. And these waveforms are doing a variety of things, and many of them are rather strictly repetitive, but many of them are not in crucial ways in order to actually do a sort of controlled evolution of the qubits themselves. Of course, I won't take you through in these last few minutes what these channels all are doing, but I'll just give you, maybe I'll leave you with one message about where the system has to be going. And one thing, I've now switched back just for these pictures to semiconductor qubits, but the message is exactly the same, which that part of it is that you have to do sort of 3D wiring. You can't just have signal flow out to the edges. And at the moment, that's where we're at, that there's some new kind of packages that you have a sort of interposer, a new chip that sits right on top of the qubit chip. And then you more or less, oops, my punchline is jumping into there. You more or less just to connect up coaxial cables right to that interposer structure. So you have many tens of coaxial cables, and you saw them. This is an old-fashioned cryostat here, but the ones that I showed you were instrumented with many, many cables. And where this is going, but it's still a long way to go, is to put all the electronic control also at low temperature. So maybe at 4 Kelvin or so. And so that the number of cables that come in from the outside world will be 1 or 2, because your quantum computer will just have an IP address, and it will be only digital high-level information that goes into the device, into the experiment, you might say. And all the conversion to precision analog will happen right at the chip. Now, this is mainly just a dream at the moment, but there are serious researchers. You have a wonderful research team up the lake at Lausanne that is busy creating the new kinds of electronics that are required to exist on such a plane. But it's a rather wide open subject of how this will get solved. And if anything, that is a harder problem than the problem of really making the million qubits on the chip. So I think with that, I will stop. So I hope you've enjoyed my survey. It wasn't a lot about quantum physics. It's more about how we will do the quantum engineering. So, and I use that to show you my bibliography of, I'd say, the high points of pedagogical literature over the years on these subjects. I highly recommend Merman's book if you're at all into quantum computing and you want to have a lovely introduction to it. But I'm going to stop there, and thanks for your attention, but I wait to see if any of you have some questions.
David, thanks a lot. Thank you very much. I applaud here. For everybody else. Actually, it's quite impressive. I mean, we had lots of talks on theoretical aspects, quantum fields, whatever, quantum algorithms, but I didn't realize that the actual technical implementation is so difficult. The scalability seems to be a real problem. I mean, to get up to.
Yeah, I mean, that's where I think, I dream about the concept that the people who have the right mindset for this are the people who have made your detectors.
Mm. Mm-hmm. Yeah, the complexity is maybe similar, but the size is quite different.
Size is not ever going to be that big. I agree.
Speaking about size, just as a question of interest, what are the microwave frequencies involved here?
The sweet spot is around 6 gigahertz. It's so-called X-band, and that has to do with the fact that there's very good precision instruments in that band due to all the industrial needs, I mean, cellular needs. And it's a comfortable temperature. It's comfortable from the temperature point of view. That is, at 10 millikelvin, basically all excitations are frozen out in a system operating at 6 gigahertz, excuse me.
Okay, so I'm sure that there are questions from the audience. So there's so many quantum interested people at CERN. I'm sure there should be some questions. Yeah, here's one. Okta?
Yes, hello. Thank you very much for the nice presentation. I was looking at the slide where you showed the huge dimension only of the controlling installation for a quantum processor. And I was thinking about the first classical computers who had the same problem, who were filling one floor of a building for doing what today you can do with the, I don't know, with the Raspberry Pi.
Mhm.
Do you think the research to push also in the part which is controlling the qubits, because for the classical computer, the solution was to miniaturize the device, but now obviously it's not the case because it's already quantum, it's very small. So should it be pushed rather in the technology for controlling the qubits?
Yes, and that is indeed where this is going. That and that's what I was sort of implying schematically here. That is that if we can do this, I mean, there's several stages of this, I would say, but one thought you might have is that here's a chip, and if you look at say a millimeter size region of this chip, you'd like that to do the function of a whole rack instrument. I don't have any pictures of that, but typically the signal generators, to connect to one of the channels of these instruments takes a rack instrument. I'm gesturing with my hands, and but the relevant functionality of that instrument can be replicated in a chip, of a couple of centimeter size. So that's definitely one step in that direction. Now, at the moment, such things only work at room temperature, but that's already a significant improvement, and that's in fact part of the sort of proprietary aspect of Google's work is that they apparently already have done this step, and they, for their 53 qubit supremacy experiment, they apparently don't use off the shelf instruments, microwave instruments at all, that they do in fact have custom chips. And they do say that this has definitely lowered their expenses, made it feasible for them to do these experiments.
Okay, thank you.
Okay, then there was Igor.
Hi. It's a bit provocative question, but I have a good acquaintance who is actually working, who is actually making quantum computers at one of these big behemoths that you mentioned. And once he dropped a line with me saying, never mention to me anything about Majorana fermions, because we don't believe that they will ever be useful for quantum computing. What would be your comment on that?
Well, the theory says that they can be. The theory insists upon some very, very complex materials preparation. That is, devices that hybridize, that are mashups, that are hybrids of multiple things at the same time, materials with strong spin orbit coupling, and ones that superconductors that can survive high magnetic fields and things like that. And so that field has been, having a rocky time, having a rocky start, but it's not only at its start, of course, because the experiments that reported Majorana excitations were 8 years ago now, or so, but it has to be admitted there's been little progress towards advancing from that to a definite qubit. So the people who work in that field have not been capable of demonstrating one two-level system of the type that is confidently predicted by theory. So I think one of several things might happen. Eventually it may turn out to be right. Such things have happened in physics before. To merely not having something work for 10 years is not a sign that it's a bad idea. It's a sign that it's a difficult idea, admittedly. And the other, the behemoth which has really been behind it, Microsoft, has indeed been impatiently expecting that it would achieve these milestones, make a qubit, and then it would already have a lot of the error correction concepts built right in of Kitaev. So it would already leap to the front in some sense from the point of view of topological protection. But it hasn't worked. So, and I'm not betting on it.
Thank you.
Okay, next one is Andrea.
Yeah, so I was wondering how critical is the first amplification stage next to the qubit array? I mean, do you need ad hoc amplifiers developed on purpose, or can you live with commercial ones?
They are, at least at the present stage of development, quite crucial. I'll give you a few things about this since you ask. You should understand, I'm a theoretician, but I'm the kind of theoretician who pays a lot of, pays a lot of attention to, you know, the details of how experiments work. Let me go to here. So, let's see. So this, whoops, geez, I'm in a strange mode here. Let's try it this way. Yes, that's better. It turns out, come on. This is the amplification chain. It actually also involves this device. This is already an amplifier, but it's a really special purpose amplifier that you know, is itself a piece of research, basically a Josephson parametric amplifier. There have been great leaps in those amplifiers. You know, they have things like noise temperatures as figures of merit, and these have noise temperatures, you know, in the far sub-Kelvin region. It is necessary to have a whole chain of amplification, and this one is now a sort of semi-commercial one, high mobility transistor amplifier, which has a noise temperature of a few Kelvin, and which you know, can be bought, but is also not a very conventional amplifier. The rest of this is very conventional, you know, rack amplifiers. So there's still indeed progress to be made, and in programs we're working on, there are still new milestones of how to make new varieties of these first stage amplifiers.
Thank you.
So
Next one is Vincent.
Hi, thanks for a very nice talk. So on the, I think it was slide 13, where you're talking about, I guess, crosstalk between qubits that shouldn't or aren't physically connected via some coupling.
yeah.
Is this, so in your paper, is it focusing mostly on the quantum aspect of crosstalk, or is this like a classical explanation? And is there a way to better protect from crosstalk in that, you know, better shielding between the couplings and so forth?
Okay, well, yes, is the short answer, but okay, but let me fill that out a little bit. That yes, what I was saying is that the interaction we care about here is a quantum mechanical interaction. You know, it's a term in a Hamiltonian. But our claim is that, at least in the setting that we're in, that term in the Hamiltonian, the coefficient of that term in the Hamiltonian is determined by pure classical physics, but not simple classical physics. It's, you know, whole, you know, basically microwave physics of this chip. I believe this does provide guides to how to lower these unintended couplings, which is basically to make these transimpedances smaller. So you have to now think like an engineer, and how do you get rid of, it's a crosstalk, you know, from the point of view of a microwave engineer, it's a crosstalk question of how to get rid of these transimpedances. And yes, indeed, the right kind of packaging, you know, conducting planes above and below, certainly moves you in the right direction. And that's now well understood, that you should not have this chip out in the open, so to speak, even in the open inside the cryostat, that it should be really tightly packaged with carefully thought through conducting packages, superconducting packages to make these classical crosstalk quantities smaller. And that will fix your quantum mechanics. That's our message.
So, okay, if I may just follow up quickly. So is this something that's more like a hardware based or engineering, as opposed to something that could be necessarily or potentially corrected in some way using smart algorithms or software?
Yes, it is possible. It's indeed quite possible that at some level it can be corrected by, quote, software, which can indeed either mean, well, there's either sort of quantum control techniques where you I mean, you have other terms in the Hamiltonian that you can turn on and off by applying pulses of radiation on purpose from outside. And they can be designed to steer around these imperfections if you know what they are. That always takes some overhead, but we have groups at Jülich that are quite busy with that. And then the other version of that is then in the end, if you don't have any good schemes for doing that, then try for this topological protection, try for redundancy in your algorithm that will be more generically immune to these kind of imperfections.
Great. Thank you very much, David. Very nice.
Okay, thank you, Vincent.
So there are some questions typed in the chat. Angelo is asking, thanks for the very interesting presentation. I have a question. Isn't it possible to leverage signal multiplexing techniques to reduce the overhead of readout electronics?
Yes, and that's there are situations where that's straightforward and is being done. It turns out the readout lines can be moderately multiplexed, and that is a technique that's, I believe the Google chip had sort of 8-to-1 multiplexing in readout. The idea of multiplexing is hindered by the fact that these are in fact very high precision operations. I mean, I barely talked about that, but you need to deliver classical microwave pulses to activate. I showed a few waveforms, and you can ask what are the noise figures of merits on those waveforms, and they are quite stringent. So any multiplexing you do has to respect that. People are making progress on that. I talked about the grand idea of multiplexing, which is to do everything digitally as much as possible, as close down to the chip as possible. And put all your A to D converters and D to A converters very close. That would be a very big multiplexing in the sense that you would reduce the cable count out of the instrument from hundreds to 2 or something like that. But such multiplexing is being thought about at many levels, but it hasn't worked that much. I mean, that is to have the precision. High precision still means, a channel per qubit in many labs.
Okay, so I say thank you for Angelo. Now Curtis asks, how's the noise threshold related to the time required to complete a calculation, and why is it 10 to the 14? Why is a 10 to the 14 increase necessary?
Well, that 10 to the 14 is it should be understood. It's not anything you have to do physically, so you don't have to improve the basic quantum physics, the precision of the basic quantum physics by 14 orders of magnitude. I think that deserves a whole talk, and I mentioned some names. I mentioned people like John Preskill, who would probably be a great speaker for you sometime, who could indeed spend an entire talk explaining why topological protection is such a great thing. I guess from a solid state point of view, it's closely related to why the quantum Hall effect is such an enormously precise phenomenon, which then finally has to do with the fact that tunneling over a long distance can be exponentially small. So you can easily get 14 orders of magnitude reduction of tunneling amplitudes in quantum Hall physics. Now, this is more sophisticated. That's just the protection of a sort of single parameter. That is the fact that the Hall resistance is a von Klitzing constant to 13 decimal places, and we have to translate that into a whole dynamical process that is made precise to that level. So that's just to say that there are a whole set of concepts developed, which I don't think I should say any more about, but it is seriously believed to be possible. And I know Google gears up to have experiments that will start to show that it's possible in the laboratory.
Okay, thank you. Then a question by Christos. This is also a question of foreseeing the future, but some major points, topics that we can expect to see and will be improved in the near future?
Sorry, didn't understand that.
Neither. I think he just asked for what are the major points.
Oh, okay. Now I'm reading the chat. That makes it easier. Well, in the near future. Okay, that's a good question. Well, there are many developments. Okay, one not scientific one, but important for us is that we're trying to take this out of the domain of just mega corporations and actually do this in a public partnership in Europe. And that's being benefited by the climate in the research climate in Europe and also in Germany, actually, where they're willing to give this a shot and put quite a bit of resource into doing this. But we'll spend a few years just catching up, excuse me, with Google. As I said, I think a trend is that engineers need to get seriously involved. That is, but it can be the kind of quote engineers that you have at CERN, who know all about instrumentation and timing and performance of analog devices and in unusual conditions. That we just need a lot more of that to further progress. Maybe I'll leave it at that list. I mean, it could be a longer list.
Okay, thank you. Then Marek. Marek, you have raised your hand.
Hear me now? Still there, no problems with the Zoom.
Can you speak louder?
I hear something.
Okay, so you can hear me. Okay, so this is a very opinionated question, I guess, but what do you think those quantum computers, if they materialize in, let's say, reasonably near future, I don't mean immediately, but like what kind of, let's say, within your lifetime, or let's, as an example, will actually be useful for? Because I mean, like the standard thing, we could talk about show algorithm breaking RSA and so on and so on, but we're already in the process of developing quantum resistant encryption algorithms. So I personally don't believe that those computers will make that much of an impact on crypto as there are some people claim they might. But so what do you think actually will be the main point for those machines,
Okay, well, I'll give a very unorthodox answer to that. The main point will be to make computational mathematicians incredibly happy. The ones who have spent their lives learning, for example, exploring the Riemann hypothesis, which has involved enormous amount of computing, and the symbiosis of large computation and new insights into number theory has been a pretty fruitful one, and I think could be given a big boost by that. Now, that is the most politically incorrect answer I can possibly give you, because, and I'm hardly allowed to say it in any of my professional company, because they would say that's the way to kill quantum computing, because we don't do things just for curiosity. We do things because we're going to make people money. And you did say the near future. So probably I haven't answered your question, and I have no idea whether it's really true that we could improve quantum chemistry by the phase estimation algorithm of quantum computing, or whether that could be, at all interesting in a small number of years. People have proved that you can, with quantum computing, solve the H2 molecule. Well, that's not super exciting to me. I learned about solving the H2 molecule when I was in graduate school with the codes I had 45 years ago. But I'll stop there. I mean, I think there is a reason to be excited about quantum computers, but it's not for mere short-term lucrative benefits. Marek seems unimpressed.
Well, I would say we the particle physicists are very much used to this question. Anyway.
Well, while working on particle physics, I would say that doing something because it would be exciting to do that is not an uncommon, a completely alien subject. So we won't tell anybody who said that.
Unfortunately, physics has many, many such possibilities of spending a lot of money to satisfy curiosity. So we unfortunately do have to be selective about these things.
So there are no further questions. I just would like to give a comment. I mean, if we go back like 50, 60 or whatever years, there was once, I think, some Intel person, somebody was asked what is the use of this, the market for computers, and he was saying, I think, he believes worldwide that there's a capacity, there's a need for 5 computers or something.
Yeah, that's a quote from the president of IBM at that time.
Yeah, so I think that's a good way to conclude this beautiful talk and the discussion. Thanks again very much.
Yeah. Okay, thank you for the discussion. It was very nice to interact with you. And until the next time, whenever that would be.
Yeah, so if you happen to be around or in the region or whatever, after pandemic, then please.
Okay, thank you. Well, actually, I'm going to be, quote, in Lausanne next week because there's a summer school there. The organizers were thought in the winter that they would make it in person, and I said not likely, and indeed we won't.
This doesn't help because we are still closed.
Yeah, exactly. Right. Okay. So, oh, you mean CERN? I couldn't come in the gates anyway. Yeah. Okay, I'm going to leave.
Okay. Thank you. Thank you very much. Bye-bye.